This section, we are focusing on understanding the mole concept and molar mass, looking at Avogadro's numbers and calculations, looking at the molar mass of a compound from its formula, calculating the amount and the number of moles of a compound from a given mass and vice versa, and then using Avogadro's number to calculate the number of atoms or ions in a compound. And I love these. Holy moly! What do you get with a mole of avocados? You get guacamole. Mole problems, just call, we're going to learn that 1 mole of anything is 6.02 times 10 to the 23rd. And I love this guy. This is Avogadro. Hey, I just met you, and this is crazy. But here's my number, 6.022 times 10 to the 23rd. So call me maybe. I know, I'm a nerd. Let's get going. Okay, so the mole concept. All right, our mole is the center piece here. This is our mole roadmap. We're going to learn that we can go to mass and mass to moles. We can go to particles or atoms or ions and back to moles. We can get to volume of a gas and back to moles. First, let's understand what a mole is. Have you heard of a century? A bike race that's 100 miles, or a century is 100 years. So we can group and just say a century bike ride, and we know automatically that it means 100 miles. We know that eggs you buy in a carton, we just say a dozen eggs, and we know that that's 12 eggs. I could say a dozen cars. That means 12 cars. If I had a dozen pencils, you would know that I had 12 pencils. So a dozen is a grouping that 1 dozen of something is equal to 12 of them. Say I had a pair of shoes. You would know that 2 shoes were involved in that pair. A pair of socks means that you have 2 socks. So a pair generally means 2. So let's practice doing a conversion, knowing the dozen. So we'll write 2 forms of the conversion factor that will help convert a dozen to number of eggs and number of eggs to a dozen. Well, we can say that 1 dozen, I'm going to abbreviate here, dozen, is equivalent to 12 eggs. Or we can say that there's 12 eggs in 1 dozen. Okay, so let's use one of those conversion factors to convert 3.75 dozen eggs. So 3.75 DZN into eggs. So similar to when we did metric conversions. What do we want? Eggs. What have I got? Got dozen. So I want the conversion factor where eggs is on top and dozens on the bottom. 12 eggs, 1 dozen. So now I just need to multiply across, divide going down. So 3.75 times 12 divided by 1 should give me 45 eggs. And dozen will cancel out, leaving me with those eggs. Now let's convert 248 eggs and figure out how many dozen that is. So what do I want? I want dozen. What have I got? Eggs. So I'm going to use this guy, that 1 dozen is 12 eggs. So 1 dozen on top, 12 eggs on the bottom. So eggs and eggs will cancel. So I'm going to do 248 times 1 and divide it by 12 to get 20.7. I'm going to write it over here to the left. 20.7 dozen, because that's my unit left. And I started with 3 significant figures, so I'm going to end with 3 significant figures. Okay, so you get the idea of the dozen. 1 dozen, 12 eggs. Well, 1 mole is 6.02 times 10 to the 23rd. Atoms, particles, molecules. Those are all kind of used interchangeably, okay? In 1 mole. So we've got 1 mole of carbon contains 6.02 times 10 to the 23rd carbon atoms. 1 mole of water contains 6.02 times 10 to the 23rd water particles, or water atoms, or water molecules. Okay, so 1 mole of something is 6.02 times 10 to the 23rd. It's a huge number. That number is equal to 602,000 times a million times a million times a million, which is 602 hexillion, which is 602 with 3, 6, 9, 12, 15, 18, 21 zeros after it. If you tried counting this, it would take you 20 quadrillion years to count to a mole. Obviously, this has not been done, but I'm sure that somebody was timed counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 for, I don't know, a certain amount of time, and then times that by 6.02 times 10 to the 23rd, and it would take 20 quadrillion years. I have some other interesting facts about a mole. If we had a mole of donuts, okay, stacked on top of each other, it would reach from the sun to the earth and back 200 billion times. If I had 1 mole of softballs, the volume of that many softballs would be about the size of the earth. If I had 1 mole of Olympic shot put balls, it would have the same mass as the earth. Here's a crazy one. If 1 mole of pennies were distributed equally among 6 billion people, each person would get 1 times 10 to the 14th pennies, or 1 times 10 to the 12th dollars, which is equal to $1 trillion. Can you imagine? Each person, so 6 billion people dividing 1 mole of pennies, and each person would have $1 trillion. So we have a new conversion factor here. 1 mole of something is equal to 6.02 times 10 to the 23rd atoms of it, or particles, or molecules. Or we can flip it around and say 1 mole of it has 6.02 times 10 to the 23rd of it. Now, this 6.02 has been reduced because this kind of looks like pi, right? 3.14 da 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 da. So we are simplifying and using 6.02. Sometimes in some questions you might see it say 6.022. It just took it 1 digit further. I do have, so when we talk about the mole, this also pops into my mind. Now, this scene from a movie is from Austin Powers. I don't know if you've seen it before. It's a pretty funny movie. And this is just a short clip.
Your chair, Dr. Evil.
Thank you. Whoa! A boo. Thanks.
Skedaddle.
Wow. Now that's vital information.
I know, it's amazing.
Oh, Basil. What's happening, baby?
A lot is happening, Foxy. Dr. Evil has escaped. The good news is that one of our agents has managed to infiltrate Dr. Evil's organization.
Excellent, Basil. We've been trying for years to get a mole inside Dr. Evil's lair. We now have that mole.
Yes. Ah, and here he is.
So you're the...
Most excellent agent we've ever seen.
Yes, most excellent agent we've ever seen. Thank you.
Thank you. Now, I wasn't able to get an exact location, but I did learn that Dr. Evil has moved to a new lair outside of Tokyo, Japan. By the way, I realized that I have a large mole on my face.
Where? What? Where's that mole? I didn't see one.
I also realized the irony that I am myself a mole.
No one would make that connection.
Anyway, well done, old chap. Jolly good work.
Yes, nice to mole you. Meet you. Nice to meet you, mole. Don't say mole.
Stop.
I said mole.
Stop.
Bye.
Mole. Mole. Mole.
Oh, shut up! Molly, 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 Molly.
So, I've been assigned to welcome you to the Ministry of Defense. I have a letter from my director personally thanking you for switching sides. I can't wait to inform Austin of your defection. There you are. I'll come to tell you the good news. Mini-Me has switched sides.
Ah! Oh. Sorry about that, old chap. Sorry. Sorry. Welcome aboard. My mistake.
What was that? Listen, just get it out of your system.
No, I'm fine.
I insist. We could work together better if you just got...
Mole! Bloody mole! We're not supposed to talk about the bloody mole, but there's a bloody mole winking me in the face. I'm gonna chop it off and cut it up and make some guacamole.
Better?
Yeah.
All right, I know that was a ridiculous scene, but makes me laugh anytime I see it and think about Avogadro's number, ironically enough. So let's set up an actual example here. We want to know how many sodium atoms are in 0.240 moles of sodium. And I can't stress enough how important it is to label. So we want to say down here we need 1 mole of sodium. Okay, right? Because we need moles and moles to be diagonal from each other. And so what do we want? We want atoms. So we know that there's 6.02 times 10 to the 23rd atoms of sodium and 1 mole of sodium. Now I'm going to show you how to set this up on your calculator. All right, so here I have my graphing calculator, and I'm going to type in 0.240, and then I'm going to do times. Now I need to do 6.02 times 10 to the 23rd. I'm going to zoom out here real quick. I'm going to type in 6.02. I'm going to hit second, and this number above my 7, actually not second, sorry. The button above my 7 is EE. Some calculators might make you do second in EE, but notice that it says 6.02 E23. That stands for 6.02 times 10 to the 23rd. You hit enter, and our answer should be 1.4448 times 10 to the 23rd. I only want to end with 3 significant figures, so I'm going to go 1, 2, 3. So 1.44 times 10 to the 23rd. I'll show you on another calculator I have here. All right, here I've got just a regular scientific calculator. I'm going to do 0.240 times, and then I'm going to type in again here 6.02. Now this EE button, I have to do second EE, so that also that button above the 7, so 6.02 E23. I can hit enter, and this should also tell me the 1.4448. Notice where it says times 10 to the 23rd power. So I only want 3 sig figs, 1.44 times 10 to the 23rd. All right. Now, let's do another practice problem. Can you try to set this up? Setting it up using our unit analysis or dimensional analysis. How many moles of aluminum are in 3.42 times 10 to the 21st atoms of aluminum? So why don't you pause this video here real quick and set it up. All right, now hopefully We started with our atoms of aluminum. What do I want? I want moles of aluminum. What have I got? I've got atoms of aluminum. So we can cancel out those atoms of aluminum because they're diagonal from each other. And we know that 1 mole is always 6.02 times 10 to the 23rd. So in this case, in my calculator, I'm going to type in 3.42 times 10 to the 21, times it by 1, and divide it by 6.02 times 10 to the 23rd. And check, you should get 5.68 times 10 to the negative 3. You might have gotten, your calculator might have done this in decimal form because we know that 5.68 times 10 to the negative 3 is 123.00568 moles of aluminum. Either one of those answers is fine. I'll type it into my calculator just to make sure that you got it correct as well. All right, let's make sure that you're comfortable with typing in dividing two numbers that are in scientific notation. So I'm going to type in 3.42 times 10 to the 21st power. And we're going to times it by 1. So if you want to do that, but we know that that's going to give us the same number. And then divided by 6.02 times 10 to the 23rd. And see, this calculator gives it to me in decimal form. If I want it in scientific notation, you can actually have this calculator do it for you. And you can just hit second and then this button right next to it where it says psi, and go to psi and look 5.68 times 10 to the negative 3. And then if you want it back in decimal point form, you can just hit second and then go back to flow, and it'll put it in decimal point form. All right, I'm going to have you do a couple practice on your own here. So pause the video and try to solve these two problems, and I'll put the answer up in just a moment. How did you do? Did you get the right answer? Pause the video here to look at how I set it up if you need more time. All right, so what we have just been working on is this section here, going from moles to particles using this conversion factor, going from particles to moles using this conversion factor, knowing that 1 mole is 6.02 times 10 to the 23rd. Now, we can also use a mole relationship to go to the mass of a substance. And to do that, we just refer to the periodic table. The molar mass is how much 1 mole weighs in grams. So look at the periodic table. Get that in front of you if you don't have it in front of you. 1 mole of sulfur weighs 32.065 grams of sulfur. 1 mole of, let's look at magnesium, is 24.305 grams. So I'm going to give you a relationship. Let's say I have 1 mole of something. We know that's 6.02 times 10 to the 23rd things of it. Well, so let's say if I had 1 mole of sulfur, 1 mole of magnesium, I have the same number of it. But I just said that sulfur weighed 32.06 and magnesium was 24.305. So if I have 1 mole of magnesium and 1 mole of sulfur, they weigh different? Think of it this way. What if I had 10,000 M&Ms, 10,000 jelly beans, 10,000 chocolate malted balls? Well, 10,000 M&Ms only weighs 8,770 grams. 10,000 jelly beans only weighs just over 27,000 grams. And wow, 10,000 chocolate malted balls weighs 154,000 grams. Think of it this way. This is why if I have the same number of sulfur atoms, carbon atoms, and zinc atoms, 1 mole of each of them is going to weigh differently. And we can see that on the periodic table from that average atomic mass, which we will now call molar mass. When we say if I have 1 mole of sulfur, it has a mass of 32.07 grams. 1 mole of carbon is 12.01 grams. 1 mole of zinc is 65.38 grams. So take a minute and pause this video and find the molar mass for each of the following elements. And double check with what I have. So to get into the definition. The atomic mass of any substance expressed in grams is the molar mass of that substance. So I can say the atomic mass of carbon is 12.01 AMU, average atomic mass units. So therefore, the molar mass of carbon is 12.01 grams for 1 mole of carbon. Now, for our diatomic elements, remember Brinkelhoff, if there's 2 nitrogens, I need to have 14.01, which is on my nitrogen mass, or depends on what periodic table you're looking at. The one I'm looking at is 14.007 grams for 1 nitrogen. I need to multiply that by 2 because N2 is 2 nitrogens. Now, what if I want to find the molar mass of a substance or a compound, like morphine? Morphine has a formula of C17H19NO3. Morphine is used to treat pain, although it's highly addictive. Tolerance develops with long-term use. So to find the molar mass of a compound, I simply need to take 17 carbons and times it by what carbon's molar mass is. 19 hydrogens times it by 1 nitrogen. 1 hydrogen. 1 nitrogen times it by nitrogen's mass. 3 oxygens, and then add them all up. So this would be the average atomic mass unit, which we can then say the molar mass is 285.313 grams for 1 mole of morphine. All right, so you try this. Calculate the molar mass for ammonium gas, which is NH3, sulfur hexafluoride, and magnesium nitrate. And check to see if you got the same answers I did. So let's look at what a mole of different things look like. Aspirin, whose formula is C9H8O4, its molar mass is 180.2 grams for 1 mole. Copper 2 chloride dihydrate, so adding up this molar mass would be 1 copper, 2 chlorines, 4 H's, and 2 O's, giving me 170.5 grams per mole. Iron 3 oxide, here's an example of 159.7 grams per mole for that compound. And water, H2O, 2 H's and 1 O, has a molar mass of 18.02 grams per mole. So let's do an example here. What is the mass of 1.33 moles of titanium? So I'm starting with 1.33 moles. Right? And what do I want? I want mass, which is grams of titanium. What have I got? I've got moles of titanium. Okay, and remember, for every 1 mole, we just need to look at the periodic table and see what the molar mass is. And here's how it would look. My molar mass of titanium, 47.867. Again, if you're off, if that 3rd digit is off, or if there's 4 on your periodic table, it's okay. I started with 3 significant figures, so I'm going to end with 3 significant figures. Try this one. Try setting this up, and we'll check back in just a minute. This one was a little tricky. Did you get stumped? Well, I started with atoms, and it wanted me to get to mass. So I started over here. This is a 2-step problem. I needed to go from atoms to moles, and then moles to mass. So let's look how we set this up. So my very first step, I started with atoms, so I had to get to moles. So I went from atoms to moles using my 1 mole over 6.02 times 10 to the 23rd atoms. So that got rid of atoms, that leaving me with moles. So what do I really want? I really want grams. What did I temporarily have? Moles. So notice diagonal moles of lead and moles of lead cancel out. So I had to set up 2.55 times 10 to the 23rd times 1 times 207.2 all divided by 6.02 times 10 to the 23rd. And I started with 3 sig figs, so I'm going to end with 3 sig figs. Check your answer, see if it matches. All right, let's try this guy. I've got 2.25 grams of fluorine gas. I want to know how many molecules is present in that much. Why don't you pause this and see if you can do this two-step equation now. How did you do? We started with grams of fluorine, so I went from grams to moles, and then moles to particles. 2 steps. If you wanted to separate them and do just this first step, so 2.25 times 1 divided by 38, hopefully, did you remember to multiply F's molar mass by 2? If you wanted to see what that equals and then go from moles to molecules, that's fine if you wanted to do it in 2 steps. You'll get the same answer, 3.56 times 10 to the 22nd molecules of fluorine. All right, I have 3 more challenging ones for you. So pause and work through these, and let's see if our answers match at the end. All right. Yes, take a minute, and if you need to pause, check your answers, and see if everything matches. I've got a few more for you here. How many magnesium atoms are there in 150 grams of magnesium? If you're feeling comfortable with this, feel free to just skip on ahead. You don't need to do all of these if you're feeling really confident in it. Here's another problem, and I love it when problems do this. How many grams of chromium are there in 25.1 grams of chromium-3 acetate? So normally we would have to go, okay, chromium is Cr, this 3 is a +3. Look at your polyatomic ion sheet, figure out what acetate is, and C2H3O2 with a -1 charge, so that'd be Cr1, and then acetate 3. So we would have to derive this, but this is given to us. And then in addition to that, if we've got grams, we got to get to moles. So we have to find the molar mass of this and add up 6 carbons, 9 H's, 6 oxygens, and a chromium. But they gave it to us. So I love it when problems come with that. So why don't you pause and see if you can figure out how many how many grams of chromium are there? So this is a little bit tricky. We want to find out how many grams of just chromium is in chromium acetate. So let's look at how we did this. We went from grams of chromium acetate, grams to moles of chromium acetate. Now look, in chromium acetate, in 1 mole of chromium acetate, there is 1 chromium. So we can say that there's 1 mole of just Cr. Now, what if I wanted to know how many grams of oxygen is there in 25.1 grams of chromium-3 acetate? For 1 mole of chromium acetate, there are 6 moles of oxygen. So this would be a 6 on top here. Or if I said how many grams of hydrogen? Well, how many hydrogens are there in 1 mole of chromium acetate? Well, there's 3 times 3 is 9. There's 9 moles of hydrogen. So that would be on top here. And then we would do 1 mole of chromium and then look at getting to grams of chromium. So look at the periodic table. So these, again, if you want to pause and take the time, if you feel like you want some more practice, the answers are on the right. So just cover up the answers and try to solve them. Okay, let's do a few of these join-ins. Which of the following elements has the largest molar mass? So pause and check out those elements. You should get AS. Work through this. If you have 0.25 moles of each of the following elements, which one has the largest mass? That'd be zinc. Which sample has the largest number of atoms? Oh, so we got to go from, if they're in grams, grams to moles, moles to atoms. If it's already in moles, you just need to go to atoms. Which one has the largest number? Pause it and find it out. You get 10.5 grams of iron. What's the approximate molar mass of iron 2 oxide, FeO? The molar mass of methane is 16. Which one represents the greatest number of molecules of methane? 35 grams. And that concludes Chapter 2, Section 6.